Hello, my name is Matthias Scheffler and I am from the NOMAD laboratory in Berlin, which is hosted by the Fritz Haber Institute of the Max Planck Society and the Humboldt University. It is a pleasure and honor to present a plenary lecture at this International Conference on Materials for Humanity 2021 and to talk about value creation from data, specifically about big data and statistically exceptional materials. What do I mean by this title? Prosperity and lifestyle of our society are very much governed by achievements of condensed matter physics, chemistry and material science because new products for the energy, environment, health, mobility, IT sectors and so on largely rely on improved or even novel materials. Several examples are discussed at this interesting conference. The enormous amounts of research data produced every day in this field represent a gold mine of the 21st century. However, this gold mine is of little value if these data are not comprehensively characterized and made available. How can we refine this feedstock that has turned data into knowledge and value? For this, a fair data infrastructure is a must. I guess you know the acronym FAIR. It stands for the request that research data should be findable, accessible, interoperable, and reusable. Only then data can be readily shared and explored by data analytics and artificial intelligence, AI methods. Making data findable and AI ready is an alternative and forward-looking interpretation of the acronym FAIR. It will change the way how science is done today. Let me describe the challenge that is eluded by this needed AI readiness of data and by the title of my talk. So considering the about 100 atoms of the periodic table of the elements and all possibilities of mixing these atoms in all possible structures and unit cell sizes implies that the number of all possible materials is practically infinite. This implies that it is very likely that materials exist that we don't know so far, and that these materials have novel properties, or they have a performance in their function which is better than that of the materials we know today. Or it may be that some known materials have properties that have not been recognized so far. So how can we find these exceptional materials? We will get important information from high throughput experiments or computations. But in view of the sheer size of the chemical and structural space of material, this direct information will remain very insufficient. The daunting challenge for artificial intelligence for material science is that in this practically infinite space, the interesting materials are very rare. The interesting materials, that is, the materials with a high performance function, are statistically exceptional. A route towards solution is to create maps of materials, properties, and functions. These maps rely on the knowledge of the appropriate coordinates. The two axes of this figure, here on the x-axis the descriptor D1, and on the y-axis called descriptor D2, these are physical parameters that are initially not known. Only if we have found the appropriate descriptors, we may discover such a map where in relatively small areas there are materials that are good, for example, good superconductors. In other areas, there are materials which are good for photovoltaics and so on. In my talk, I will show how this coordinate system, that is the two or more descriptors, can be found by artificial intelligence. The goal is pattern discovery for uncovering physical characterization. This also means that we like and need to achieve some understanding. We like to identify descriptors that are explainable or interpretable. And in this tutorial picture, I plot the material property Y as the function of the material's descriptor D. Machine learning employs a global model. That is, it uses one single model to describe the whole population. It therefore minimizes the overall prediction error using regularization. This means that we disregard local details on purpose. Thus, with these great data points and using a global model, here a linear regression, the best fit looks like this. The first method that I like to advocate in my talk is subgroup discovery. And I like to acknowledge Mario Bolai and Yildiz Vreken, who have introduced us to this concept. The point is that there may well be more information behind these points. The points may be red and blue, but this information is not known to us. Nevertheless, the correct, that is meaningful fit would be this. These are two distinct subgroups. This is the science we like to recover in the data, and with this we also get a better and meaningful description. In this case, even orthogonal to the global model. As I said, we may not know that the data points are red and blue, but we hope that AI can help us to find out. Here is another tutorial picture for the same problem, now addressing the point that we are interested in materials that exhibit a statistically exceptional behavior. These are about 1,000 data points, and now we have two distinct descriptors, D1 and D2, and we have a property Y that can have two values, circle or square. How can we find structure in the data? If you look at it, you may be able to identify something immediately. Here is a region where we have only squares. Obviously, we want that such identification is achieved automatically. Let me emphasize that this pattern is only visible if we plot the data as a function of these descriptors D1 and D2. With other descriptors, this structure may not show up. Thus, we also need that the coordinates, that is the descriptors, are found automatically. This is what subgroup discovery is doing, finding the coordinates and finding the patterns. In more mathematical words, we like to find Boolean conditions, also called selectors, which may be combined into a conjunction. And we like to maximize a quality function which addresses our target property. This quality function needs to be defined by us because it defines the property of interest, for example, the band gap of a semiconductor. However, the Boolean conditions and the coordinate systems are not defined by us. They need to be identified by the subgroup discovery procedure. For this tutorial picture, I noted three different conjunctions, sigma A, sigma B, sigma C, that define three different groups. Two subgroups are 100% pure, A and B, and here is one that is not pure but dominated by squares. Let me mention one example of a quality function, but there are many others. The example is the information entropy. So P is the probability to find a certain value, that is circles in a subgroup. Simply speaking, this is the percentage of circles compared to all data points in the subgroup. And this probability is multiplied with a logarithm of the same probability. When the subgroup is pure, that means 100% circles or 0% circles, the entropy is 0. This is what we like to achieve as good as possible. Finding a subgroup which is as pure as possible, maximize the negative entropy. This is just one example of what can be a component of the quality function. Let me now demonstrate this with a specific study, turning greenhouse gases into useful chemicals and fuels. This work was done together with these gentlemen. CO2 is typically considered a bad gas. However, at some point, CO2 may well be an important raw material for the creation of fuels and valuable chemicals, as indicated here. There are different routes towards the formation of methane and methanol, which are used for heating, for fueling cars, and so on. And there are several other important chemicals. This here is just a selection. This all is possible already today, but the process is very inefficient. We need a better catalyst, and I'd like to show you how subgroup discovery may accelerate the process to find one. We have looked into metal oxides because oxides are typically cheap and stable. We looked at the stoichiometries noted here, and we considered materials like manganese, calcium, strontium, barium, aluminum, and so on and so on. These are many different materials. Catalysis happens at surfaces, thus we also had to considered various surfaces of all these materials. How can we find which surface and which material is a potentially good catalyst, and therefore should be studied in more detail? We did not calculate the full catalytic process. We have done such studies in the past, and we learned that the many aspects that rule heterogeneous catalysis are too intricate, and that a full theoretical description does not make much sense. Alternatively, we will ask which material activates CO2. This concept of activation is well established. CO2 is bad for the atmosphere because it is very stable. A stable molecule needs to get prepared for the desired chemical reaction. In the gas phase, this is achieved by charging the molecule. This weakens the CO bonds, and it is visible by a change of the geometry of the molecule from linear to bent. This bent molecule will then happily do a chemical reaction. So the idea in surface science was that we need materials where the adsorbed CO2 molecule looks as shown here. As I said, this was and is understood to be the first but necessary step of the catalytic conversion. This was the idea. Surfaces which promote such a geometry may be a good catalyst. Other surfaces don't need to be considered. Now, in our study, we looked at activation with less prejudice, and we considered 5 different scenarios that may be indicators of a weakening of the chemical bond. An alternative idea to the bond angle would be that the bond length is increased. Obvious, another indicator of weakening the bond. There are other possibilities, but because of time, I will only concentrate on these 2 ideas, bond angle and bond length. In the publication, you find more. The subgroup discovery analysis now goes as follows. We first have to define the target property. So let's say that we choose target number 1. We like to find the subgroup of materials for which adsorbed CO2 will develop a small OCO angle. Then we have to define the quality function that should be maximized for this target. Here you see what we have done. There is a cutoff telling that we only like to look at systems that have an angle smaller than 132 degrees. The gas phase inert molecule has 180 degrees. We're saying the angle should be smaller, and in fact we say it should be even smaller than 132 degrees. We also want that the size of the subgroup should be as big as possible under the other constraints, and we have a condition which takes care of the Sabatier principle. The Sabatier principle tells if the binding of the CO2 molecule to the surface is too weak, the molecule would not stay there, and if the binding would be too strong, the molecule would have no reason for doing another chemical reaction. Thus, the bond strength between the molecule and the surface must be intermediate. For this requirement, we use the information gain that I had mentioned earlier. So this is the quality function for group 1. For the other target, we have another quality function. Let's have a look, let's look at both cases and let's see how we can find the coordinate system, that is the descriptive parameters that identify the subgroups. We use 46 different features, potential descriptors such as free atom properties and properties of surfaces, hoping that at the end our scheme will select 4 or 5 of these many features as being relevant descriptive parameters. In simple words, we offer essentially everything that we felt may be or could be relevant. These basic features characterize the clean materials surface. The answer, which of these 46 features are actually important and what should be their range, is then determined by the mentioned quality function and the Monte Carlo scheme. And here is the result. These are all the systems we have calculated, displayed in terms of the OCO angle and the CO bond lengths. Thus, the coordinates here are the 2 quantities we are interested in. The blue subgroup is the small OCO angle subgroup, and the green subgroup is the large CO bond length subgroup. In the coordinate system of this plot, the blue and the green dots are scattered. They don't look like groups. Obviously, the group character is not defined by these coordinates of this plot. The red line, by the way, is the result for the gas phase CO2. There, the bond length and the bond angle are correlated. Obviously, this is no longer the case for adsorbed CO2. The descriptive parameters that identify the 2 subgroups are not the coordinates that are used in this plot, but they are noted here with the selectors of the subgroups. Thus, for the small angle subgroup, the blue one, we have the charge of the surface oxygen atom of the clean surface, the energy of the maximum of the p density of states of the surface oxygen atom, the kurtosis of the O to P density of states of the surface oxygen atom, the maximum value of the 2 ionization potentials of the 2 free metal atoms, the minimum value of the 2 radii of the HOMO radial wave functions of the 2 free metal atoms. As you see, these are free atom and clean surface quantities, and they characterize the catalyst material. They are not directly related to the catalytic reaction of the CO2 bonding or the CO2 bonding, but they identify the materials that may be good catalysts. These descriptive parameters are also called materials genes, as they correlate with different mechanisms that trigger or actuate, but maybe just facilitate or maybe hinder the different processes which play together, very much as genes in biology. And for the green subgroup, we have other descriptive parameters or genes, as noted here on the right side. Please check the publication preprint at the archive for more information. As I said earlier, evaluating the efficiency of a realistic catalyst numerically and reliably is not really possible. There are too many processes which play together in a very intricate manner. So having identified the subgroups, we now looked into the experimental situation. There are not many experiments which have studied the catalytic performance of these systems in sufficient detail. Just 7 experiments can be used, but we can conclude from them that the good catalysts belong to the blue and some to the green subgroup. So the conclusion is, when searching for more efficient catalytic materials, one should look at the materials which are defined by the selectors of the blue or the green subgroups. There's a good chance to find the high-performance materials in these subgroups of the whole material space. The other materials will probably exhibit a lower performance. So this is what I meant with pattern discovery for identifying statistically exceptional structures and physical characterization. There is a deluge of data. In the previous examples, this was so for the theory, but not so much for the experimental situation. The relevant data in material science are typically, in fact, not big, but just a small fraction of the whole population, and we recommend to identify these relevant data first, and only study or fit or machine learning those. Subgroup discovery does not mean that we are collecting individual outliers. We are identifying subgroups, which means we identify a coherent subset of data that are defined in a concise description. We also call this rules. The primary features of these rules are analogous to genes in biology. They relate to the properties and processes that they may trigger, activate, facilitate, hinder the material's function of interest. We have looked with this methodology into several systems and several functions to build maps of materials' properties. The role model of our ideas is largely the concept Mendeleev had when he were creating the periodic table of the elements. He knew about 60 atoms, but with his table he could predict the existence of other atoms, and he could even predict their properties. Ashby plots in engineering are another role model. We looked into crystal structure prediction, and here you see a map of materials. I don't tell you here the x and y coordinates, that is the descriptors D1 and D2. They are given by properties of the free atoms. If the descriptors refer to a point in the red region, the corresponding material will crystallize in the zinc blended structure. If the two descriptors point to the blue region, the crystal structure is predicted as rock salt. We also looked at oxides of the group 3 elements. These are transparent metal oxides, aluminum, gallium, indium oxides with all stoichiometries and compositions. And we looked at perovskites. There's a very famous Goldschmidt tolerance factor. It's an empirical factor which tells about the stability of these systems. With our methodology, we could derive a related factor, but different to the Goldschmidt factor, which has a much higher reliability above 90%. We looked at the activation of CO2. This is what I've shown you already. We looked at property classifications, for example, topological insulators, and the question if and how free atoms carry the information that the created solid will be metal or insulator. We are actually employing two different methods for these questions. The subgroup discovery is one of them, and I've described that already, but we also have another method, which is called SISO, Sure Independent Screening and Sparsifying Operator, which is a combination of symbolic regression and compressed sensing. SISO is often more powerful, not always, but often more powerful and also more quantitative than subgroup discovery. In many cases, thus it may be advantageous. And on this slide, I compare standard machine learning with compressed sensing and symbolic regression. In both cases, one aims at a good fit or an interpolation of known data points and to build a function to express the material's property P as a function of some descriptor describing the material. The key scientific challenge is to find a reliable descriptor. The importance of this descriptor finding is often not really appreciated. And because there may be hope that with sufficiently high number of data, the choice of the descriptor may be not so relevant. We, in fact, emphasize that the descriptor is very important to get a reliable and also interpretable result. And for that, we favor symbolic regression, which means that we use analytic functions as potential descriptors. Let's have a look at the standard machine learning here at the left, where we write the desired function in terms of a sum over Gaussians. This is kernel-rich regression with a Gaussian kernel. And there are typically many thousand of these Gaussians. The descriptor tells about the distance between data point, and using the known data, we have to determine the initially unknown many thousand coefficients, Ci. The coefficients are determined by the request that the predicted value should be close to the known value. On the right side, we have the compressed sensing and symbolic regression concept, which we are favoring. This looks like a linear model, but the known linearities need to and are captured by the descriptor. The property at the function of the descriptor is then just a scalar product of the vector that contains all the offered descriptors and the initially unknown coefficients. So P equals D1 times C1 plus D2 times C2 plus D3 times C3, and so on and so on. As before, we request that the prediction should be close to the known values. For the construction of many descriptors, we use a hierarchical approach to build functions of basic features. So we use features as, for example, the 46 features we had mentioned earlier in the CO2 catalytic example. But then these features are added or subtracted or multiplied, squared, put into an exponential, cubed, and so on and so on. And then, in a further one, this combination, these already treated features are again combined by many mathematical operations and so on. This gives a huge number of functions. And as I said, each of the functions is a potential descriptor and enters as one element of this vector D. To avoid overfitting and to make the whole procedure stable, one introduces what is called regularization. In kernel-rich regression, the regularization is written down here. This is like a Lagrange constraint with a parameter lambda that ensures a smooth fit, and it ensures that the prediction accuracy is close to the training accuracy. As you see here, the regularization depends on the L2 norm. That is the norm that we know as a standard norm, or the length of a vector. In complex sensing, one is using a constraint, the so-called norm 0. The norm 0 is the number of known zero elements. So the request on the right side here is to find the best coefficients, Ci, under the constraint that most coefficients should be 0. This means that at the end, from the many descriptors that we offer, only very few will survive, because most of them are multiplied by 0. In this way, we get a good fit and select the most relevant descriptors. The approach can also be called descriptor or representation learning, and our descriptors are analytic functions. This is why the procedure is termed symbolic regression. We had started that concept several years ago with Luca Geringelli using lasso, which we had combined with the L0 optimization. Now, typically, sparsification by the norm 0 is numerically nearly impossible, as it represents an NP-hard problem. And therefore, lasso and typical compressed sensing approaches use the L not the L0 norm, but approximate the L0 norm by the L1 norm. We found ways that this approximation is not necessary. There's another problem with lasso when the number of descriptors is getting too high and or when the descriptors are correlated. Our CISO approach also solves this problem. CISO, by the way, stands for sure independent screening and sparsifying operator. We can use several 100 billion potential descriptors, and correlations don't hurt too much. At the end, CISO selects out of this immensity of descriptors candidates, just one or two or three analytic functions that describe the property of interest. 1 to 3 out of many, many billions. Maybe one additional word about the comparison between left and right. Standard machine learning needs a lot of data. The more data, the better the description. CISO does not need big data in terms of results. It needs a big number of descriptors to choose from. Only if the offered pool of descriptors contains the needed function, the needed materials genes, we will achieve a good fit. More data will not help. Only more or more appropriate descriptors. So let me show one example of such a CISO study. This is the catalytic conversion of propane to acrylic acid. And it is an example of a purely experimental study. Thus, although I am a theoretician, we don't use any density function theory data here in the study, but only experimental information. As we have very few experiment data, it is truly important that the data are of high quality and they need to be fully characterized. We also say that quality and full characterization together means we need clean data. We need fully characterized data, and unfortunately this is not often found in the literature. But here our experimental co-workers, Annette Trunschke and Robert Schlögel, and their co-workers have done a most impressive job. So let's look into this example. Clean experiments and artificial intelligence for an important catalytic process. This is the experimental setup or workflow. The first step is the catalyst synthesis and catalyst preparation. Here we are dealing with a fresh catalyst. Clearly, the catalyst material would typically change when it is under reactive conditions or reaction conditions. Catalysis is a highly dynamic and complex phenomenon. It is not a stable thermodynamic situation. So the system changes, and this is termed here activation. We have an activated catalyst, and then the experimentalists study the catalytic activity. And this is done systematically using common characterization techniques, but also methods which are not so common in the field, and the latter are therefore called advanced characterization, and it means that the material is studied under the actual working condition. The important point is to have a detailed characterization of the fresh and of the activated catalyst materials. So, very fast, the measured quantities and the methods are noted here. There's X-ray diffraction providing information about the crystal structure, and N2 adsorption is used to study or to provide information about the mesoscopic structure. Information about bulk and surface properties are gathered, and about the chemical behavior of the surface. And in the advanced characterization, Trunschke et al. Measured the conductivity of the sample under the reaction, surface property change, and they looked at surface property changes in dry and wet in carbon feeds. So we then use all these experimental data as primary features to combine them in the symbolic regression. Altogether, these are, by the way, 49 different quantities measured as a function of temperature. As I have, or the selectivity or the reactivity is then measured as a function of temperature. As I've told you before, we then analyze the catalytic performance, and we want to do this for the conversion of propane. Now, as in many catalytic processes, these chemical reactions are not one way. For example, using propane and adding oxygen, you can form acrylic acid. This is the first line. This is the process we are interested in. However, propane can also form propylene, or it can burn completely to CO2. This is not what we want. We are only interested in the first line. Thus, we are looking for a catalyst that has a high selectivity towards acrylic acid formation. And this is the result of our CISO analysis. A map of the wanted selectivity. The color code tells, or is as follows: yellow is very low selectivity, not good, and dark blue or violet reflects very high selectivity. So we want, of course, high selectivity towards the formation of acrylic acid. From all the many billion equations, our descriptors, we then analyze by CISO and do the selection, and at the end we find the descriptor D1, which you see here on the y-axis, and the temperature is on the x-axis. Altogether, this shows us the map of selectivities. The descriptor is actually two-dimensional, and we only show a cut of the D1, D2 temperature result. The black lines, dotted, dashed, and full, are the experimental data of 7 vanadium-based catalysts. Thus very few, but with CISO we get the result for the full range. The green line is a specific prediction. Here you see the descriptor which CISO has found and which is used on the y-axis of this plot. It depends on very different materials' properties. For the green line, we have changed the pore volume, that is a mesoscopic structure of the fresh material. As said before, we offered 49 different primary features, and you see that 7 have been selected. These are properties of the clean and of the activated catalyst material. And knowing this descriptor tells us what we have to change to improve the catalytic performance. So we identify with CISO the quantity, or quantities, you can also say the screws, which we have to turn to improve the catalytic performance. And here are the screws. The volume of the pores of the catalytic material, the activation energy of the bulk conductivity, the work function, the surface vanadium content, and the surface carbon content. Let me conclude with a look at one of our websites. Several years ago, we started the NOMAD repository, where we invited everyone who is doing computations to upload their data. Recently, we started to add also experimental data, but so far, NOMAD is clearly dominated by computations. There, NOMAD now has more than 100 million calculations. We don't want to make the uploading complicated. It should be as simple as possible. Therefore, data should be uploaded the way they are produced by the used computer code. Essentially, every computer code which is important is accepted and served. If a new code isn't there yet, we are happy to write the needed parsers together with the code developers. The uploaded data are then parsed and normalized, and this makes the data fair, and this is what is called the NOMAD archive. We then have an encyclopedia to look at the archive, and we have what we call the NOMAD Artificial Intelligence Toolkit. Everything I told you today, that is the artificial intelligence tools which we have used for subgroup discovery and CISO, you can find here as Jupyter notebooks. You can play with this, you can modify the notebooks according to your own needs to see how you may actually use them. So this is all on the webpage. Get started with the Artificial Intelligence Toolkit tutorials. We develop and implement methods that identify correlation and structure in big data of materials. This will enable scientists and engineers to decide which materials are useful for specific applications, or which new materials should be the focus, of future studies. The following tutorials are designed to get started with the Analytics Toolkit. In this talk, I've shown you examples how to find relevant materials genes and what screws need to be turned to change materials in a way that they have a better function and a better behavior. With Nomad, we started a culture of sharing, accepting all different computer codes, but we think there is need for a next level of sharing because AI methods in the literature are often not fully documented with respect to the used data and with respect to some details of the method. So we invite people to publish the data and also the AI code. As for the data, we will provide a DOI, a digital object identifier, so things will be citable, and Nomad will certainly help to create these Jupyter notebooks. You have seen the people who were involved in the studies when we are going through the different examples, but there are many, many others who work in very similar or related work. Many people have contributed to these various developments. In particular, I'd like to mention again Luca Giringelli. And with this, I thank you very much for your attention.